Bismillahirrahmanirrahim. Assalamu alaikum class. Today we are going to discuss about some conceptual questions and their answers in SN mechanisms. I'm Dr. Aisha Farooq here to solve all your problems related to SN mechanism. The question number one given in your assignment was the label the following reactions as SN1 and SN2 or neither. Okay, and your options were A, B, C, and D. Your first reaction, reaction A, CH3Cl plus sodium hydroxide gives us CH3OH plus NaCl. This reaction is classified as SN2 reaction because of primary alkyl halides. In your next reaction, there is a tertiary alkyl halide, that is why it is classified as SN1 reaction. The next reaction is CH through CH2I plus AgNO3 gives us a CH3CH2NO3 plus AgI. This reaction is neither SN1 nor SO2. It involves only ion exchange of ions and is classified as an ion exchange reaction because of the nucleophile. Okay. Next reaction is CH3 CH2 CH2Br. Again, this reaction is classified as an SN2 reaction. Always remember the classification of reaction as SN1 or SN2 always depends on the reaction mechanism and the nature of reactants. SN1 reactions involve a unimolecular substitution process, while SN2 reaction involves a bimolecular substitution process. In some cases, the reaction may not fall in either category. Okay. Your next question was to identify the nucleophile, electrophile, living group and the type of SN mechanism for the following reactions. That was very simple. जो भी आपका एजेंट लगा होगा आपकी अल्काइल ग्रुप के साथ वो आपका लिविंग ग्रुप होगा. एंटरिंग ग्रुप जो कि आपका साथ में सेकेंड रिएक्टेंट होगा वो आपका न्यूक्लियोफाइल होगा. और फिर आप उसमें से बताओगे कि रिएक्शन आपका प्राइम SN1 था या SN2 था. तो इसमें मैंने बारी बारी सबको यहाँ पे हाईलाइट कर दिया है दोनों स्लाइड्स पे. पहली स्लाइड में है CH3 आयोडाइड प्लस हाइड्रोक्सल आयन गिव्स अस CH3OH यानी मिथाइल अल्कोहल, साथ में आयोडीन रिलीज हुआ है तो न्यूक्लियोफाइल हाइड्रोक्साइड आयन है. इलेक्ट्रोफाइल इसमें मिथाइल आयोडाइड है, मीन्स आपकी सबस्ट्रेट. लिविंग ग्रुप आपका आयोडाइड आयन है और SN मैकेनिज्म जो फॉलो यहाँ पर हो रहा है दैट इज SN2 मैकेनिज्म. इन द रिएक्शन बी यहाँ पर आपका इलेक्ट्रोफाइल है टर्शरी ब्यूटाइल क्लोराइड, न्यूक्लियोफाइल है आपका साइनाइड आयन, लिविंग ग्रुप है क्लोराइड आयन और ये मैकेनिज्म भी SN2 के तौर पे कैटेगराइज किया गया है. In your next reaction, ethyl bromide is your electrophile, hydroxide ion is your nucleophile, living group is bromide ion. Again, this reaction is an SN2 mechanism. In both reactions A and C. Okay, nucleophile attacks the electrophilic carbon resulting in the substitution of the living group iodide or bromide ion, and there is the formation of the product that is either your methyl alcohol or your ethyl alcohol. These reactions follow the bimolecular SN2 mechanism. For reaction B, the nucleophile attacks the electrophile carbon of the tertiary butyl chloride, resulting in the substitution of living group chloride ion and the formation of product, again tertiary cyanide. That is why this reaction also follows the bimolecular SN2 mechanism, because it is not disturbing the stereochemistry of the it is disturbing the stereochemistry of the reaction. Remember, SN1 and SN2 mechanism always differ in that terms of reaction rate and intermediate formation. SN1 reactions process involves with the formation of a carbon intermediate. In the above reactions, again that was a very interesting question that provide the missing reactants and product, and I have given you the reactions, and in the next step I have completed all these reactions. You can check it out. If anyone has a problem in that, you can also ask me on my number given to you. Your question was the reaction between 1-bromobutane and sodium methoxide predominantly proceeds via the SN2 mechanism. This is due to the absence of a bulky leaving group and the presence of a strong nucleophile which favors a bulky biomolecular mechanism. This reaction between 1-bromobutane and sodium methoxide, the SN2 nucleophilic substitution is involved. This is attributed by two factors. The first one is that there is a no bulky leaving group was present over there. 1-bromobutane has a relatively small and non-bulky leaving group, bromidine, which allows the nucleophile to approach the electrophilic carbon atom without steric hindrance. Bulky leaving groups hinder the nucleophilic attack, favoring the SN1 mechanism instead of that. The second reason that it follows the SN2 mechanism was the presence of a strong nucleophile, that is sodium methoxide. That is a strong nucleophile due to the presence of the negatively charged oxygen atom and relatively high basicity of methoxidine. And the strong nucleophilicity promotes the direct attack of the nucleophile on the carbon atom, leading to the SN2 mechanism. Overall, the absence of a bulky leaving group and the presence of a strong nucleophile in the reaction between 1-bromobutane and sodium methoxide make the SN2 mechanism the predominant pathway for this reaction. Your question number 4 in your assignment was the compare and contrast SN1 and SN2 reactions in terms of reaction rate, stereochemistry, and the nature of living group. And you have to give the specific example to support your answer. So here is the answer. SN1, it depends on the concentration of substrate, and SN2 always depends upon the concentration of substrate and nucleophile. Okay. SN1 has a slow rate of reaction while SN2 is a fast rate of reaction. SN1 have intermediate step while there is no intermediate carbocation formation in SN2. Stereochemistry of SN1 reaction can lead to racemization or the formation of a mixture of enantiomers, while SN2 reactions proceed with the inversion of stereochemistry, resulting a single enantiomer or a single diastereomer. Living group, in order of the comparison of living group, SN1 reactions tolerate weaker living groups such as halides and sulfonates. SN2 reactions require better living groups such as halides or phthalates. Your question number 5 was that determine the major products and provide the detailed mechanism between following reactions, that is 3-ethyl 3-methyl pentane when it reacts with ethane thiol in the presence of a strong base. So reaction between 3-ethyl 3-methyl pentane and ethane thiol proceeds via an SN2 mechanism, and the major product is 3-ethyl 3-methyl pentyl ethyl sulfide. Question number 6 was the explain the concept of neighboring group participation and provide an example of an SN2 reaction involving NGP mechanism. Neighboring group participation involves the participation of neighboring functional group in an SN2 reaction, aiding the bond making and bond breaking process. An example is group in an SN2 reaction aiding the bond, an example is the reaction between 2-bromo, 2-methylpropane and hydroxide ion in the presence of silver oxide, where the neighboring methyl group helps to facilitate the SN2 reactions. Your question number 7 was the consider the reaction between benzyl chloride and hydroxide ion in an aprotic solvent. Discuss the likely mechanism and any factor that might influence the reaction outcome. So the answer to this question is the reaction between benzyl chloride and hydroxide ion in an aprotic solvent is likely to proceed via an SN1 mechanism. The presence of resonance stabilized carbocation intermediate, that is benzyl cation, and the absence of a good nucleophile favor an SN1 pathway. So factors such as stability of carbocation and solvent polarity can influence the reaction outcomes. That is why this reaction proceeds via SN1 mechanism. Question number 8 was draw the structure of all possible constitutional isomers for a compound with the molecular formula C4H9Br. Predict which isomer is most likely to undergo an SN1 reaction and explain your reasoning. The answer is that the constitutional isomer for a compound with the molecular formula C4H9Br are 1 bromo 1 methylbutane, 2 bromo 2 methylbutane, 1 bromo 2 methylbutane, 2 bromo 3 methylbutane, 1 bromo 3 methylbutane, and 1 bromo 4 methylbutane. The 2 bromo 2 methylbutane isomer is most likely to undergo an SN1 reaction due to the stability of the resulting tertiary carbocation intermediate. It also causes the steric hindrance to the nucleophile. That is why that it is not going to support SN2 mechanism. Your question number 9 was to consider the reaction between tertiary butyl bromide and sodium iodide, predict the major product, and provide the detailed mechanism for the reaction. So, answer to this question: the reaction between the tertiary bromide and sodium iodides leads to the formation of tertiary butyl iodide as the major product. Mechanism for this reaction is an SN1 process. It will proceed in three ways. First step 1, first of all, ionization of tertiary butyl bromide is occurred to generate a tertiary butyl carbocation. In step 2, there is a nucleophilic attack of iodide ion on the carbocation. And in step 3, there will be deprotonation by a solvent molecule to form the tertiary butyl bromide. In question number 10, explain why primary alkyl halides are generally more reactive in SN2 reactions compared to the secondary or tertiary alkyl halides. Provide a specific example to support your answer. So the justification for this is that they are generally more reactive in SN2 reactions because of the steric hindrance. This steric hindrance किसकी होती है, which is caused by the substituent groups in secondary and tertiary alkyl halides, which hinders the approach of nucleophile. In contrast, primary alkyl halides have fewer substituents and allow better access for the nucleophile. For example, the SN2 reaction between methyl iodide and hydroxide ion proceeds rapidly, while the reaction between tertiary butyl bromide and hydroxide ion is significantly slow due to steric hindrance. Describe the effect of solvent choice on SN1 and SN2 reaction. Provide examples of solvents that favors each mechanism and explain the reason behind their influence. The choice of solvent can significantly influence the preference for SN1 or SN2 reactions. Solvents that favors SN1 reactions are typically polar protic solvents such as water and alcohols. These solvents stabilize the carbocation intermediate through hydrogen bonding and facilitate ionization of the substrate. Solvents that favor SN2 reactions are typically polar aprotic solvents such as acetone, dimethyl sulfoxide, and acetonitrile. These solvents do not stabilize carbocation and allow better nucleophile access, promoting bimolecular reactions. Your question number 12 was that discuss the effect of nucleophile strength and the rate and outcome of SN reactions. Provide examples for your different nucleophiles and explain their impact on reaction kinetics. So the answer to this question is nucleophile strength has a significant impact on the rate and outcome of SN reactions. Strong nucleophiles such as hydroxide ion, cyanide ion, and an alkoxide ion favor SN2 reaction due to their high nucleophilic reactivity. They quickly attack the electrophilic carbon and displace the Lipin group. Weaker nucleophiles such as water, alcohols are likely to participate in the SN1 reaction. They are less reactive and favor the formation of carbocation intermediates which can subsequently react with a nucleophile. Choice of nucleophile influence the reaction kinetics and selectivity with stronger nucleophiles leading to the faster reactions and a higher likelihood of SN2 pathways. Your question number 13, consider the reaction between 1-chlorobutane and sodium methoxide, predict the major products and provide the detailed mechanism for the reaction. The reaction between 1-chlorobutane and sodium ethoxide results in the formation of 1-butanol as the major product. The detailed mechanism for this reaction is as follows. In step 1, first of all, nucleophile will attack on the ethoxide ion on the carbon atom of 1-chlorobutane, leading to the formation of an intermediate alkoxide ion. In step 2, there will be a deprotonation of alkoxide ion by a solvent molecule, generating the final product, that is 1-butanol. Your question number 14 was the explanation of the concept of steric hindrance and its impact on SN2 reactions. Provide an example where steric hindrance influences the reaction outcome. Steric hindrance refers to the physical obstruction or crowding around a reaction site caused by a bulky substituent or functional group. In SN2 reactions, steric hindrance can significantly impact the reaction outcome. When a nucleophile approaches the electrophilic carbon, it must navigate around the substituents. If steric hindrance is too high, the nucleophile may not be able to effectively attack the carbon, leading to a slow reaction rate or even inhibition of the reaction. An example of steric hindrance influencing the rate outcomes in the SN2 reactions between tertiary butyl chloride and hydroxide ion due to the presence of uh, bulky tertiary butyl groups. Steric hindrance make it difficult for the nucleophile to approach the carbon, resulting in a significantly slower reaction rate. And the very last important question of your assignment was the discussion of the role of temperature in SN reactions. How does temperature affect the rate, selectivity of SN2 and SN1 reactions? So you also have to give examples to support your answer. As we know that temperature plays a very crucial role in SN reactions, affecting both the rate and selectivity of SN1 or SN2 pathways. For SN1 reactions, if we increase the temperature generally, it will accelerate the reaction rate. Higher temperature will provide more thermal energy, leading to the increased molecular collision and higher kinetic energy. High temperature can also promote the ionization of the substrate, increasing the concentration of carbocation intermediates and favoring the SN1 pathway. However, higher temperature may also lead to the side reaction such as elimination, as the energy required for the elimination pathway can be more easily reached. For SN2 reactions, low temperatures are generally preferred because lower temperature reduce the kinetic energy of the molecules and decrease the chance of collision-induced elimination reaction. But extremely low temperature, however, can slow down the reaction rate and reduce the mobility of the nucleophiles, leading to the decreased SN2 reactivity. The choice of temperature depends on the specific reactants and desired reaction outcome. For most SN2 reactions, the moderate temperatures are often optimal. An example for this reaction is between bromobethane and hydroxide ion to form methanol at room temperature. The SN2 pathway is favored, while at higher temperatures the reaction may exhibit a high tendency for elimination to form an alkene. Remember that the specific temperature requirements and effects can vary depending on the reactants and the reaction conditions. Thank you so much. If you have further queries, you can come to me. You can subscribe my channel. I will definitely sort. Thank you so much for watching this video. If this content is very useful for you, just let me inform and tell me if I have some good suggestions to improve it.